did that on it's on Google Classroom. Again, this is the same topic that I have discussed with you in during last session. That is fluctuating stresses. What is the criteria? That is Suzerberg, Goodman, or Gerber line. Again, we have seen again which one is the best possible solution. The Goodman diagram gives the best possible solution, and why it gives the best possible. I have already elaborated and described that thing. Then we have started the two cases about the modified Goodman diagram for axial and bending stresses, and second case that is related to modified Goodman diagram for torsional shear stresses. But here, the last time I have covered the some theory part which is related to modified Goodman diagram for axial bending when components subjected to fluctuating load. I have already explained these things about the what you mean by fluctuating stress. There is a sigma mean and sigma A alternating stress or their combination, and because of that we have to modify the diagram. Again, here I would like to take a recap within 1 or 2 minutes. You know very well. And there was one question from the students I have seen later on after concluding the last session. So why SE is not taken on x-axis? One of the students asked this question. Today I would like to, if you present, I will explain this. The its question was why SE is located on y-axis, why not on x-axis? You know very well sigma m or mean stress on x-axis and amplitude stress on y-axis. Now look at the here. I am constructing one diagram. Now this is a time, or you can say this is the stress, and if it's a mean stress, suppose I am going to line. This is the main line, and you know very well when sigma mean is equal to, or you can say this amplitude, sigma amplitude is equal to 0. So what is going to become here? All amplitude means alternating stress. Alternating means it is not going to fluctuate. It remains constant. And if it is remain constant, it becomes the case of static loading. It becomes the case of static loading. And when sigma is 0 here, so don't consider y-axis, only you will having this line, or you can say that time SYT, SUT is the criteria. And we have already in earlier, the units we have seen when components subjected to static load, when it is made up of brittle material, SYT is the criteria. When it is made up of when it is made up of brittle material, SUT is the criteria. And when it is made up of ductile material, SYT is the criteria. Try to correct the statement. For ductile SYT, for brittle SUT is the criteria. That's why, and if alternating stress here, sigma A is equal to 0, if there is no alternating stress, that means component subjected to static load. And if it is subjected to static load, why to consider SU on this x-axis? No need to consider SU on x-axis. Try to understand. This is the, you can say the reason for that purpose. And again here, why SE is considered on y-axis? Another question. Again here, you know very well. I am going to again construct another diagram here. Look at this here. If component subjected to reverse load. Reverse means in reverse cycle magnitude. Suppose this is this magnitude of this stress and magnitude of this stress which are same. Suppose here, suppose this is plus 20, and again here suppose minus 20. And if you are going to find out sigma A, what you will get here, or the mean stress, sigma mean here, what you will get, sigma mean is equal to 0. I have already told. But even though if you are going to find out sigma m, which is equal to 20 plus another one is the minus 20 minus 20 by 2. Again, what you will get? This it becomes 0. That sigma mean is equal to 0. If sigma mean is 0, but it's a reverse load. And what is the criteria? I have already told you, when component subjected to reverse load, SE is the criteria, and that's why this SE is located on y-axis. I think you are getting my point. Those were asked by some of the students during last session. Why not SE on x-axis and why SE on y-axis? This is the reason. Try to understand. I will further proceed for our today's topic. Now here in today's session, what we are going to do, we have discussed the theory part. What theory part we have discussed? What do you mean by Suzerberg line? SE1 y-axis, SYT1 x-axis, line joining is Suzerberg line. Then SE2, SUT is the Goodman line. Then parabolic curve joining SE and SUT is the Gerber line. It's a parabolic one. And you can locate SYT1 x and y. Even though if you want, you can locate the SUT here. But why SUT is not located on y-axis? Because this y-axis plays important role for the fatigue failure because SE is the criteria. And I have already told if component subjected to fluctuating stresses or a load, it may fail before the SYT or may fail before the SUT. So don't no need to consider because we are going to consider SE is the criteria. Why to show SYT, SUT on a y-axis? This is the reason. This is about the last question. It's okay now. So you can look at SYT and join this. It's a yield line. Again, I have already explained to you here. So while constructing the modified Goodman diagram, you know, last time modified Goodman diagram when components subjected to bending and axial load. I am constructing further. It's from this point to this and again this point. Because if I am going to construct SC2 up to this point A and again A to this point SYT, so we are taking the care of here yield here, yield, Y-I-E-L-D, yield, because it's a yield line. That means whatever the points which comes under this area, these points are safe points, or you can say it's a safe region. And if on in another way, if you are going to say here, the component, when the point comes under this point, so you can say the components is having infinite life. Try to understand what I am saying. The point which comes in this area, suppose O, S, E, this point A or S, Y. It's a modified Goodman diagram. You can say it's a component is having an infinite life. But the component which are coming on this line and outside this is having finite life. What does it mean? That means after some period of time, when it is subjected to some number of cycles, component is going to fail. Try to understand. Component is going to fail. And because of that, we have to consider this modified Goodman diagram for bending and axial loading. Again, second thing, if we are going to consider this SE to SUT, this is a Goodman line, but we are not taking the care of these points because when it is subjected to cyclic load or a fluctuating load, so first of all, you have to check for SYT whether the yield failure of the component occurs. And later on, it goes towards this side. That's why no need to consider, it doesn't take into consideration of this, no need to consider SYT for first cycle of the fatigue. That's why instead of taking care of this area which is given by Goodman line, you can restrict it up to the A to up to SYT, and that's why this area is the modified Goodman diagram for axial or bending line. Now, I have already explained these things also with you, but today because of the last one question asked by one of the students, that's why I have elaborated these things once again to you. It's okay. Again, I have discussed with you the equation of a straight line. You know the how to find out the equation. You know very well x upon a coordinate upon intercept upon a is the intercept or x axis, y is the intercept on y axis is equal to 1. Then equation of Suzerberg line sigma m upon SYT plus sigma a by s is equal to 1. Or you can put here the value of this, you know, the sigma a mean stress. Generally, if we are taking the points here, we can write down in this fashion also. Suppose 1 minute, we will proceed. We will see the earlier slide here. Look at this here. So what we have to do, suppose on next slide, on modified Goodman diagram, I would like to explain. Look at this here, the point. Suppose I am going to use the pen. Look at this point. I have taken it. One is having the SA and the SM. And but in earlier slide, I have taken this point is, you know, if we are, it's a SA, but it's nothing but a, which is having correlation with sigma A. Again, I am taking another point SM. It is one A x-axis, but is a sigma m. But how to correlate with this? If I am going to write the equation of a suppose Goodman line, this line A B F is a Goodman line. How to write the equation of a Goodman line? Now suppose SA, suppose for this X point, SA upon what? SE plus here. What I am going to write here? SM upon SUT is equal to 1. This is the equation for this X point. But what do you mean by this SA? So we can substitute this SA and SM. You can also write down this. So what you will get? Sigma A, SA means sigma A into FOS. Try to understand. Upon SE is equal to sigma M means sigma mean into plus sigma mean into FOS upon SUT is equal to 1. You can take FOS common, and what you will get here? In the equation, or you will get sigma A upon SE plus sigma mean upon SUT is equal to 1. And here common FOS you can send toward this side, so you will get FOS. This is also the another equation for this, the Goodman line. Similarly, you can write the equation for Schusterberg line in terms of this, but you should have the relation of sigma mean and FOS, mean stress. And what do you mean by the SA and SM? That is sigma A into FOS. You know very well. This is about the relation with the factor of safety. So we are going to use such equations in our the analysis also. And this is the modified Goodman diagram when subjected to axial and bending stress. I have last time also explained this is SYT. You can locate SUT line joining SYT. SYT is a yield line. Then SE to SUT is a Goodman line. Then how to modify it? Because OAB instead of taken BF up to BC or area under this curve here. Look at this. I am going to highlight here. Or you can see the region OABC is the modified Goodman diagram when components subjected to this axial and bending stresses. This area here you will get the safe region. It's a safe region, but outside it, it's an unsafe region. So you can say these points or the life of the component under this safe region is the infinite. Component is having infinite life, and component which coming on this line and outside is having a finite line. Again, the question arises when the point which comes under this region OABC by using Goodman or modified Goodman diagram and is having a infinite life. That means what is the criteria for infinite life? I have already explained you. Endurance limit is the criteria. So you can use approximate estimation method to find out the SE. SE is equal to K into KB into KC dash or AC dash. AC dash is equal to 0.5 SDC. And when it lies on this line or outside it, that's why the life is finite life. And for finite life, what is the criteria? For finite life, SN curve is the criteria. That means even though we are going to use a modified Goodman diagram, for infinite, SE is the criteria, and for finite, SN is the criteria for the component subjected to axial and bending stresses. Try to understand. That means how we are resolving the the issues which are related to the fluctuating load problem. First of all, you have to check whether the component subjected to reverse loading or fluctuating. If it's a reverse load, two cases, finite life, infinite life. Finite life, SN curve is the criteria. Infinite life, endurance limit is the criteria. Second case, component subjected to fluctuating or alternating stress. What are the criteria? There are two cases. Component subjected to further axial and bending stress. Use modified Goodman diagram is the compulsory criteria for this. When subjected to axial and bending stress and torsional shear stress, you have to use a modified. Again, in modified, when it comes under the region of safety and the unsafe region, based on that you can decide whether you have to go for an infinite life problem or you have to use a finite life problem. And for a finite life, SN curve, infinite life, endurance limit. That is the thing which is associated with modified Goodman diagram. Again, second thing, I have here written the one equation. Suppose I would like to written here in another terms. In V.B. Bhandari's book, the different nomenclature which is used to while solving the problem. Also, sigma A is equal to or SA is equal to sigma A into FOS. So what I am going to write here, suppose SA upon SE is plus SM upon SUT. For Goodman line, I am writing is equal to 1. What I have told, what do you mean by SA? SA is equal to sigma A into FOS. I am going to write here sigma A into FOS means upon SE plus sigma means sigma M into FOS upon SUT and is equal to 1 upon FOS. You can send toward this side 1 upon FOS. So what you will get here, you can say it's a sigma A, it's a sigma M, and here you will get 1 upon FOS. Now here this FOS is the N or factor of safety. If this factor of safety, what I am going to say, try to remember and give attention. If this FOS from this equation 1 upon FOS, when this FOS is greater than 1, you can say component is having infinite life. And if this FOS is less than 1, so you can say component is having finite life. Component is having finite life. Try to understand. I hope you understood. The FOS, if it's greater than 1, component is having infinite life, and FOS is less than 1, component is having finite life. What does it mean? That's why while assuming the FOS in static load condition, we are taking the value of factor of safety is more than 1. And if it's a more than 1, we have designed the component may be static load condition. Yes, by considering SYT or SUT is the criteria. So we have designed all these things for the infinite life. Try to understand. But in fluctuating, it's not possible to do because of this load component may fail before SYT or SUT. That's why you have to define. Another one is the reason. Here is maybe infinite life or outside is the finite life. Or another criteria is 1 upon FOS. You can check. FOS is greater than 1, infinite life. FOS less than 1, finite life. This is about the modified Goodman diagram when subjected to combined fatigue failure. That is yielding as well as the fatigue for components subjected to axial and bending. I hope you understand these things properly. Now let us move. So I have already explained these things. We have derived this equation and how to, we have plotted one line OE making an angle of theta is having the slope sigma A by sigma M, tan theta is equal to, that is the slope sigma A by sigma 1. So you can locate the point X anywhere on this line or here. So sometimes if these points come inside it, you can say is having a infinite life. If it's on a line, you can say it's a finite life or outside it. Accordingly, you can locate the SA and SM and you can use the equation of line. And for that purpose, tan theta sigma A by sigma M again force upon area. I have already explained this thing line. When component subjected to maximum bending and varies this bending moment from maximum to minimum, so you can use tan theta is equal to MBA by MBM in. And sigma A is equal to SA upon FS, that I have explained. Sigma A is equal to FS into this and sigma M is equal to, you can use it. And again here what you have to do, the sigma A and sigma mean these values you have to substitute in the equation. If it is subjected to bending 32 MB upon pi d cube is the sigma M or mean. So we will see how to solve the problem when components subjected to fluctuating and alternating load and subjected to which load? Axial and bending. Today we will see this one problem. This problem, cantilever beam made of core drawn steel 40C at SUT 600 Newton per mm square, SYT 380 Newton per mm square is shown in figure. The force P acting at pre-end, which varies from minus 50 Newton to 100, 150 plus 150 Newton. Expected reliability is 90% and factor of safety is 2.5. The north sensitivity factor at the fillet is 0.85. Determine the diameter D here. Look at the diagram of the beam at the fillet cross section. Fillet means this cross section. So I will give you 2 minutes. You can write down this problem statement and draw this diagram. What is the given in diagram? It's a cantilever beam. It's fixed at one end. It's open at another end. A load which is acting P is, it varies from minus 50 Newton to plus 150 Newton. Look at this P. While constructing the diagram, you will get whether it's a problem of reverse load or a fluctuating load. Now it's a problem of reverse load or a fluctuating. Please tell me. The minus 50 to 150, that means it's a problem of fluctuating and alternating stress. And for reverse loading, it should be minus 50 to plus 50. Minus 20 to plus 20, that is reverse loading. But minus 52 plus 150 means it's a case of fluctuating load or alternating load. That you have to first of all think. And if it's a fluctuating load problem, a load which is a, that means modified Goodman diagram is the criteria. And again force P is acting at the pre-end and it varies, it is given. Expected reliability is also given. It is made up of steel fluctuating load. From this end it's 150 mm, and again what you have to do, you have to determine the diameter at this fillet. That means you have to find out this D at the fillet. That means you have to consider this portion. And again the fillet section is given this diameter 1.5 times, again fillet radius 0.2 times. So first of all, read problem statement carefully. I hope you have written the problem statement. Now I am going to, first of all, what you have to do, write down the given data. So you can write down cold drawn steel. देखो उधर आप cold drawn steel 40 C8. SUT is given, you can write 600 Newton per mm square, SYT 380 Newton per. Then force P acting, P varies, P minus 52 plus 150. You can write case is fluctuating load or alternating case. What is the criteria? Modified Goodman diagram is the criteria. Again, why I have written here infinite life, I will explain here. Because here, and the factor of safety is given 2.5. The notch sensitivity factor is given, that is small q is equal to 0.85. FOS is equal to 2.5. Reliability is 90. And here determine the diameter, because they are asking you to determine the diameter at the fillet cross section. If they are asking the diameter, but how many number of cycles, it is not mentioned in the problem statement. If it is mentioned, determine the diameter of the beam which will sustain for a number of 10,000 number of cycles. That means it's a finite life. But it's a, just you are determining the diameter. That's why it's a infinite life problem. So you can write there fluctuating load infinite life case. And for a infinite life case, SE is the criteria or endurance limit is the criteria by using modified Goodman diagram. And how to find out the endurance limit? You know very well, Ka into Kb into Kc into Kd into SE dash. Now let us see how to solve this problem. So first of all, after reading the problem, you have to decide whether it's a fluctuating load or a reverse load. We have decided it's a fluctuating because load varying from minus 50 to 1 plus 150. That's why fluctuating. Second, they are asking you to find out the diameter. And it's, if it is mentioned, find out the diameter for some cycles, that time the case becomes finite life. But it's a infinite life problem. And for an infinite life, what is the criteria? In reverse loading also, SE is the criteria or endurance limit is the criteria. Now let us see how to solve the problem. So first of all, write the given data. After writing the given data, load varies from minus 50 to 150. SUT is 600 Newton per mm square, SYT 380 Newton per mm square, reliability 90%, factor of safety 2.5, Q is equal to 0.85. The next step, what you have to do, it's a infinite life problem and fluctuating, the modified Goodman diagram and endurance limit. That 2 points are important. So first of all, find out endurance limit. How to find out the endurance limit? So you know approximate estimation method. SE is equal to Ka into Kb into Kc into Kd into SE dash. And what is SE dash? That is, it's a steel material, cold drawn steel. For steel, SE dash is equal to, you know very well, how much? 0.5 SUT. And what's about the Ka? Surface surface finish factor, Kb size factor, Kc reliability factor, Kd modified stress concentration factor. If thermal consideration is there, you can add Ke miscellaneous factor. If given, you can add Kj also to multiplied Se dash to get the value of Se. Now let us see. In this problem, it is mentioned cold drawn steel and SUT is given. First of all, locate Ka. So what you have to do? You have to use this chart tensile strength versus surface finish factor Ka. By using this factor, look at this. SUT how much? 600. And this is made up of by using cold drawn steel. Cold drawn means again here by this chart in the chart machine and cold drawn line is given. From 600 I have located the point here, and then on constructing the horizontal line you will get the K, that is 0.78. I have written here K is equal to 0.78. You have to refer the chart of surface finish factor. How to get the K? But in university examination, they have to provide directly the value, or they will provide you the chart. Try to understand. This is one thing. Second thing, again here, you have to find out the diameter of the beam. That means size of the or diameter of the beam is not given, and diameter of the beam is asked, means it's a cylindrical part. And if it's a cylindrical part, what you have to do? So you have to refer the chart. So first of all, assume, last time also while solving the problem, I have already told you, the assume diameter in the range of 7.5 to 50 mm. And here, you know very well, you have to use the chart here. When diameter is less than 7.5, kb is equal to 1. It is when it is assumed 7.5 to 50, that kb is equal to 0.85, and if it's greater than 50.75, so we are assuming diameter in the range of 7.5 to up to 50. That's why kb is equal to 85. So assuming kb is equal to 85, I have written here. Look at this. Kb is equal to 85. Then for 90% reliability, you can refer the reliability chart where it is. I have already explained last time. It's not. I have not taken here. But you know very well, if reliability is 90%, we have solved two problems based on that. The Kc is equal to 0.897. Right? Try to understand. Then what is the remaining? You know Ka, Kb, Kc, Kd is remaining. How to find out the Kd? For that purpose, first of all, find out theoretical stress concentration factor Ke by using Ari Peterson chart. Once you will get the Kt, and you have a Q, not sensitivity factor is given 0.85. You have a relation Kf is equal to 1 plus Q in bracket Kt minus 1. So Q, that is 0.85, and Kt theoretical stress concentration factor that you have to obtain from Ari Peterson chart. So we are going to find out the value of this Kt. How to find out this? So for that purpose, refer the Ari Peterson chart for this section. Look at this here. Now, whatever the given beam is having the geometry, this is small d, this is fillet radius subjected to bending. Now, here the diameter is d. The capital D by small d is given, that is 2. You can refer this line of 2. Then second, small r by small d. Small r by means this fillet radius, which is given in the problem that you have to find out. Look at this diagram here. This is small r by d. Fillet radius r is equal to 0.2 into d. The small r by d is equal to 0.2. So what you have to do? So one x-axis you can locate this r by d is equal to 0.2, and the line of d by d is equal to 2. You will get the point here Kt. On this y-axis, the Kt is equal to 1.44. So by using Ari Peterson chart for the given geometry, you can locate Kt is equal to 1.44. Once after locating this Kt, so you have a relation of Kf. Kf means fatigue stress concentration factor. The Kf is equal to 1 plus Q in bracket Kt minus 1. You can substitute Kt and Q. You will get here Kf is equal to 1.374. And again Kd, that is modified stress concentration factor, is equal to 1 upon Kf. So 1 upon 1.374, you will get 0.77. There is some mistake. It's a 0.71 something you are getting, and you can modify it to 0.72. I am going to correct this here. It's a point, say 0.71, 0.7, something like this is the value. So you can convert it into Kd is equal to 0.72. Try to understand. Now we have a value of Ka, we have a value of Kb, we have a value of Kc, we have a value of Kt. Then it's very simple to find out the AC endurance limit because the infinite life problem. Let us see. So for that purpose, we have to use approximate estimation formula. AC is equal to K, Kb, Kc, Kd into AC dash. But AC dash means 0.5 SUT, 0.5 into 600, you will get 300. You can substitute. We know K, Kb, Kc, Kd. Substitute all the values, you will get AC. AC is equal to 126 Newton per mm square. Then again, second thing, it is subjected to load, which is fluctuating. It varies from minus 50 Newton to up to 150. So at the fillet, which is the critical point where we have to find out the diameter, the MB max that we have to, maximum moment that we have to find out. The maximum moment load which is varying from minus 50 to plus 150. The plus 150 into 100 is the distance of this, the fillet up to this fillet. Look at this. This is 100. 150 into 100, you will get maximum moment here. 150 into 100, you will get 15,000 Newton mm. And MB mean minus 50 into 100, you will get minus 5,000. The max, you have a MB max, you have a MB mean. Once you have a max and mean, how to find out the moment, mean bending moment and amplitude of the bending moment. The 1/2 MB max plus MB mean, like I have already told, sigma max, sigma mean, 1 by sigma max, sigma mean. In this way, you have applied the same formula for bending moments. So find out mean bending moment. MB mean is equal to 1/2 this. You will get 5,000 Newton mm. Similarly, find out MBA amplitude. So you will get 1/2 MB max minus MB mean, MB max, and minus here it becomes plus 5,000. You will get 10,000 Newton. Once you have a MBA and MB mean, so you can draw this diagram. Look at all these points on the modified Goodman diagram. No need to construct by using the scale. Directly without scale you can construct. But SYT at 380. 380. That means it is going to make an angle of 45 degree. And this 90 degree. SC we have calculated 126, you can locate. SUT is given 600, you can locate. And locate one of the point on this modified Goodman diagram for axial or bending load OA, BC. Taking this point is SA, this point is SM. And here this is the theta sigma A by or tan theta is equal to MBA by MB mean. So you can substitute this value, you will get theta is equal to 63.43, this theta. This is the slope, tan theta means slope. So from that you will get tan theta. The again equation of line AB. What is the equation of line AB? It is suppose this point on X by considering the again here what you have to do is a 63 degree. You can measure the angle and construct the line where it comes on this BC or AB. So it is coming on this AB. That's why X. So you will get SA for a line AB is a this line Goodman line. So for a Goodman line SA upon AC plus SM upon ACT is equal to 1. So you can substitute SA upon ACT, SM by 600 is equal to 1. So what you will get? SA by SM. Again another relation here. For this point, if you are going to find out tan theta, you will get SA upon SM is equal to tan theta. And this tan theta is equal to MBA by MBA. Yeah, you know the value of MBA and MBM. You will get tan theta is equal to 2. Therefore, SA by SM is equal to 2. And you have a two equation now. Because point which is coming on AB is a Goodman line, apply equation of Goodman line, SA upon AC plus SM by ACT is equal to 1. Substitute AC 126, that is calculated by approximate estimation method. SUT which is given 600, you will get SA upon 126 plus SM by 600 is equal to 1. And I have already told how to substitute this SA. So you can say here sigma A into FOS and sigma M is into FOS. And you can send FOS this side, it becomes 1 upon FOS also, no problem. Try to understand. Then, by solving these two equations, which two equations? Which two equations? SA by 126 plus SM by 600 is equal to 1. And SA by SM is equal to tan theta, and which is equal to MBA by MBM. And you have this value, you will get 2. So you have SA is equal to 2 times SM. You can substitute, you will get SA. Or you can substitute SA, you will get SM, vice versa. Yeah, it's your choice. Find out SA or SM first. After solving these two equations, you will get SA is equal to 114.12 and SM is equal to 57.06. And once you have a SA and SM, I have already told you. So what you sigma A is equal to SA upon FOS. So you can substitute SA, FOS 2.5, you will get sigma A. But what is sigma A? 32 MBA upon pi d cube. Remember, this is very important point. 32 MBA upon pi d cube, you will get SA upon FOS. You know the SA, FOS. MBA is also know, you can easily find out D. Or another equation you can use, sigma M is equal to SM upon FOS. And what you have to do? The sigma M is equal to 32 MBM upon pi d cube is equal to SM upon FOS. It's your choice. whether to use a sigma A is equal to SA by FOS by substituting this value, for sigma M is equal to SM upon FOS, but in sigma mean, instead of taking MBA, you can take MB mean. After any one equation you can use to solve the problem, you will get the value of diameter is equal to 13.06 mm. This is the diameter after solving the equation. In this way, you can solve the problem based on when components subjected to fluctuating, but which load? Bending and axial loading. This is about the today's session. I hope you understand. If you have any query, please contact us through the WhatsApp or mail me at bbkushare@kkvak.edu.in. Thank you. I have referred VB Bandari's book, Design of Machine Element, third edition, McGraw-Hill publication, and I have